If the phrase training derecho sequence just rearranged something in how you think about severe weather risk, take a second and hit subscribe to Orbital View. We are tracking this setup in real time, and when the models update, we will be here. Drop your state or city in the comments. I want to know who is in or near this corridor and what your local grid situation looks like heading into this. I read every single one. 3 threads. A heat dome parked over the southern plains that is generating the most volatile instability boundary forecasters have flagged on a ring of fire pattern in years, and what that boundary is already producing along its edge. The August 10th, 2020 Iowa derecho. What it did to 37% of a state's crop in under 6 hours, and why that corridor is the same corridor lighting up on today's models. And the mutual aid collapse problem. What happens to emergency response, grid repair, and agricultural recovery when the second catastrophic wind event arrives before the first one has been assessed? Let's get into it.
Something is happening right now across the central United States that the standard severe weather coverage is not fully capturing. And I want to walk you through exactly what it is, because the operational data tells a more specific and more important story than the headlines do. The Storm Prediction Center in Norman, Oklahoma, the national hub for severe weather forecasting, has been watching a particular atmospheric configuration build across the plains for the past several days. What they are seeing is a ring of fire pattern. That name sounds dramatic, and it is not wrong to find it dramatic. But before I use the term again, let me tell you what it actually means in physical terms, because the mechanics are what matter here. Picture a massive dome of heat, not just hot surface temperatures, but a high-pressure ridge sitting in the upper levels of the atmosphere, parked over the southern plains like a lid on a pressure cooker. That dome does 2 things simultaneously. It suppresses convection directly underneath it, where the air is sinking and drying. And along its northern and eastern edges, where that sinking warm air collides with the moist, unstable air pushing up from the Gulf of Mexico, it creates a boundary. A line of extreme atmospheric tension, the kind of tension that, when it releases, does not release quietly. That boundary is the ring of fire. It is not a single storm. It is an environment, a corridor of conditions so volatile that organized mesoscale convective systems form along it repeatedly, each one exploiting the same thermodynamic gradient before the boundary shifts. Right now, that boundary runs from the Texas Panhandle northeast through Kansas, across Nebraska, into Iowa, and toward the Great Lakes. And the data sitting underneath it is not subtle. The SPC's Day 1 and Day 2 convective outlooks have flagged enhanced to moderate risk zones across a significant portion of this corridor. Those risk categories exist on a scale: marginal, slight, enhanced, moderate, high, and moderate risk is not language forecasters deploy casually. The area forecast discussions coming out of NWS Wichita, NWS Kansas City, and NWS Omaha are converging on the same language around organized convective mode, which is forecaster shorthand for the kind of structured storm system that produces widespread, long-duration wind damage rather than isolated cells. Now, the specific numbers underneath this boundary are worth sitting with for a moment. Surface dew point readings in the warm sector, the unstable air mass south and east of the boundary, are running in the upper 60s to low 70s Fahrenheit across Kansas and Missouri. That is extreme moisture loading. That is the fuel. And the instability metric that severe weather meteorologists watch most closely, convective available potential energy, or CAPE, is coming in at 2,000 to 4,000 joules per kilogram along the boundary in the current analysis. Among the highest values of the season, some of the highest values this pattern has produced. Victor Gensini at Northern Illinois University has spent years studying ring of fire climatology, and what his research established is that this pattern does not produce isolated MCS events the way a standard front does. It produces training sequences, and that distinction between an isolated event and a training sequence is the entire story I want to tell you today. But here is what I need you to hold right now, before we go any further into the mechanics. The corridor that boundary is marking runs directly over Kansas City, over Omaha, over Des Moines, over the agricultural heartland of the American Corn Belt at the single most vulnerable moment in the growing season. And the models are not showing one organized storm forming along it. They are showing a sequence. And a sequence along this track is categorically different, in terms of human consequence, from any single event within it. The lit fuse running northeast across the map is not a metaphor. It is what the CAPE analysis and the boundary position and the moisture data are telling you in operational terms right now. And to understand why that fuse is so dangerous, you first need to understand what happens when one of these systems ignites. Most people hear the word derecho and file it somewhere between thunderstorm and tornado. Neither of those mental categories is right, And the mismatch between the name and the reality has consequences for how seriously communities take the warning when it comes. So let me explain this the way it actually works. A derecho is not primarily a thunderstorm event. It is a wind machine, a highly organized, self-sustaining system of convection that produces straight-line wind gusts at hurricane force or above across a swath of terrain that can extend for hundreds of miles. Not the narrow path of a tornado, not the localized burst of a standard severe thunderstorm, but a continuous corridor of destruction that can be 300 miles long and 50 to 100 miles wide, maintained for 6 to 12 hours. Think about that physical shape for a second. A tornado carves a scar, a narrow, violent path that might be a quarter mile wide and 20 miles long. A derecho erases a corridor. It is not a point of damage, it is an edge. A bent blade dragging across the landscape at 50 to 60 miles per hour, producing gusts of 75 to 100 miles per hour continuously along its leading edge. The structural signature is called a bow echo, visible on radar as a bowing or curved line of intense convection. Shape is not coincidental. It is the aerodynamic consequence of what is happening inside the storm. As the convective system matures, it develops a rear inflow jet, a river of air punching into the back of the storm's core at the mid-levels, descending, accelerating, and exiting at the surface as the destructive straight line wins. The bow shape is the visible expression of that inflow. When you see a bow echo on radar, the acceleration is already happening. The wind machine is already running. No formal definition requires a damaged swath extending more than 240 miles with wind gusts exceeding 58 miles per hour. That is the floor. That is the minimum that earns the classification. The events that the current atmospheric setup is capable of producing sit at well above that floor. The benchmark is August 10th, 2020. I am going to spend more time on that event in a few minutes because it is the most precise historical precedent for what this corridor is facing. But the numbers alone are worth establishing here. The KDMX NexRad radar in Des Moines showed a classic bow echo structure with a 60-mile wide leading edge at the storm's peak intensity. The Marion, Iowa ASO station, automated surface observation, recorded a peak gust of 112 miles per hour. That is the wind speed of a Category 2 hurricane. Sustained across a corridor, not a point, a corridor. Now, Robert Johns and William Hurt established the formal derecho definition in their 1993 paper in Weather and Forecasting. And one of the things that paper did was distinguish derechos from other severe convective wind producers, specifically because the scale and duration are fundamentally different from what most people imagine when they hear severe thunderstorm. The NOAA Storm Data publication for August 2020 documented what 112 miles per hour sustained across that swath actually means for power infrastructure. Approximately 900,000 power poles, transmission lines, and associated hardware down across Iowa, with some segments requiring complete reconstruction rather than repair. 900,000. Let that number sit for a moment before you set it down. The reason I am spending time establishing what a single derecho does is not academic. It is because the question driving this investigation is not how bad is one of these. The question is, what happens when the second one comes? Because along this boundary, under this pattern, the atmosphere does not produce one. It has a documented tendency to produce a sequence. And to understand why, you need to understand the mechanism that makes the ring of fire a conveyor belt rather than a single event producer. The word training in the context of severe weather has a specific meaning that is worth unpacking because it is not intuitive. When meteorologists say a storm system is training over a location, they mean that successive cells or organized systems are moving through that same location one after another along the same track, the way train cars follow the same rail line. The track doesn't move, the trains keep coming. In the context of a ring of fire setup and a mesoscale convective system sequence, training means something with higher stakes. It means that the atmospheric boundary responsible for generating the first organized convective system remains in place long enough to generate a second one, and potentially a third. Each one riding the same instability corridor, each one targeting the same geographic swath, each one arriving before the debris from the previous event has been cleared, before the power lines have been touched, before the grain bins have been assessed. Here is the physical mechanism. The heat dome, the high-pressure ridge anchoring the ring of fire, is not moving on a 24 or 48-hour timescale the way a typical frontal boundary would. It is quasi-stationary. The upper-level flow pattern, the position of the jet stream, the trough ridge couplet steering the atmosphere, is locking the boundary in place. And as long as that boundary stays quasi-stationary, the thermodynamic environment that generated the first MCS reloads. The reload mechanism is the low-level jet. Every night across the southern and central plains, a nocturnal wind maximum develops at the 850 millibar level, roughly 5,000 feet above the surface. During ring of fire setups, that low-level jet routinely achieves wind speeds of 50 to 60 knots, transporting warm, moisture-laden Gulf air northward and recharging the warm sector overnight. Think of it as a pipeline running beneath the atmosphere, a pipeline of warm, unstable Gulf air that refills the tank between storms. The first MCS exhausts local moisture as it moves through. The low-level jet replenishes it within 12 to 24 hours. The boundary is still there, the fuel is back, and the assembly line runs another train. Victor Gensini and Walker Ashley published work establishing that ring of fire patterns produce training MCS sequences in approximately 38% of cases, where the boundary remains quasi-stationary for more than 48 hours. 38%. That is not a fringe scenario. That is approaching a coin flip. And the current GFS and ECMWF model ensembles are both showing the boundary holding its position for 72 to 96 hours, well inside that window. The historical case is right there in the recent record. In May of 2024, Iowa and Illinois experienced 3 organized convective systems in approximately 60 hours, tracking along essentially identical paths across the same corridor. Each event was covered as if it were a separate story. Each warning was issued as a separate product. And communities in the damage zone of the first event were still without power, still with roads blocked by debris, when the second and third systems arrived. The compounding nature of that sequence received almost no attention in the national coverage. But the operational meteorologists watching it understood exactly what they were seeing. The rail line doesn't move. Every train rides the same track. And the track underneath this current setup runs directly through the infrastructure that supplies a significant portion of the American food supply, and the power grid serving millions of people across the central United States, at a moment when both are maximally exposed. That exposure is not abstract. It is geographic and specific. And the next thing I need to show you is exactly what sits underneath this corridor, because knowing what the storm targets is as important as knowing what the storm does. Pull up a map of the central United States and trace the forecast track from the Texas Panhandle northeast through Kansas, across Nebraska and Iowa toward the Great Lakes. Now look at what sits under that line. Wichita, Kansas City, Omaha, Des Moines, Chicago in the far northeast range of the corridor. These are not rural counties with sparse infrastructure. These are major metropolitan areas with millions of electricity customers, dense urban grids, and bulk power transmission corridors that serve a much broader region than the cities themselves. And the transmission infrastructure carrying that power across the plains, the high voltage lines running northeast from Kansas through Iowa, was predominantly installed in the 1960s and 1970s. The American Society of Civil Engineers 2023 Infrastructure Report Card put the average age of U.S. transmission lines at 42 years. In the Midwest corridor under this forecast track, there are segments operating well past 60 years, past their original designed service life. These are not systems that fail immediately under load. They are systems that have been maintained, repaired, and extended through successive events. But maintenance and extension are not the same as replacement. And a structure that has absorbed decades of thermal cycling, ice loading, and wind events carries cumulative fatigue that does not show up in a visual inspection. An aging transmission grid is like a network of old bones. It held up through the last storm. That does not mean it was designed to hold up through the next one before it healed. Now, alongside that grid vulnerability, consider the agricultural calendar. The crop growing in those fields right now is at a stage that severe weather researchers at Iowa State University Extension call the single most vulnerable window to wind damage. Corn reaching the VT stage, the tassel stage, the moment of maximum height before grain fill begins, is a 6-foot stalk with a sail at the top and nothing but a root ball holding it to the ground. At VT, a derecho does not bend the crop, it snaps it. Wind damage at this stage, what agronomists call lodging, destroys a plant that looked healthy 24 hours earlier. The grain fill that would have produced the harvest never happens. The entire season's investment in that acre is gone. The USDA National Agricultural Statistics Service tracks crop progress weekly. Iowa, Illinois, Nebraska, and Kansas, the states directly under or adjacent to the forecast corridor, together produce approximately 55% of U.S. corn output. And the timing of this atmospheric setup lands squarely in the window when the most vulnerable growth stage aligns with the most volatile atmospheric configuration. Roger Elmore at Iowa State University Extension has studied corn lodging extensively, and what his research establishes is that wind-induced lodging at or near the VT stage produces crop loss rates that approach total field loss in the most severely affected areas. This is not partial damage. This is not reduced yield. This is a field that was fully invested. Seeds, fertilizer, labor, time, producing nothing. The Energy Information Administration data on Midwest grid topology shows that Iowa and Illinois combined serve approximately 6.4 million electricity customers through transmission infrastructure that crosses the forecast corridor. 6.4 million people whose power supply runs through lines that are, in some segments, 60 years old, in the path of a training derecho sequence during a summer heat event. The infrastructure story and the agricultural story and the population story are not separate threads. They are the same thread. And the best way to understand what that thread looks like when it breaks is to go back to the one time, the most recent time, when a single event along this same corridor was allowed to run to full expression. At approximately 12:30 in the afternoon on August 10, 2020, a convective system that had been organizing in South Dakota began its acceleration into Iowa. What happened over the next 14 hours produced damage numbers that at the time of the event had no modern parallel in U.S. derecho history. I want to walk you through this not as a data summary, but as a sequence. Because the sequence is what makes it a preview of what the current setup is capable of delivering. By early afternoon, the Bow Echo was fully established on the KDMX NEXRAD radar in Des Moines. The leading edge of the system was 60 miles wide and moving at roughly 60 miles per hour northeast. At the Marion, Iowa ASO station, the recorded peak gust was 112 miles per hour. That reading is not a forecast, it is a logged observation. 112 miles per hour of straight-line wind, sustained across a corridor, produced by a system that most viewers outside Iowa had never heard of before that afternoon. Cedar Rapids, a city of approximately 135,000 people, lost power to approximately 65% of its population within the first hour of the storm's passage. Not because the grid was poorly maintained. Because 112 miles per hour of straight-line wind applied across the 60 miles of transmission infrastructure produces a level of simultaneous damage that no utility anywhere in the country has the on-site resources to address at once. The damage was not concentrated. It was everywhere. The storm swath ran 770 miles from its initiation in South Dakota through Iowa and into Indiana. 770 miles of wind damage documentation, all connected, all from a single event, all in under 6 hours of peak activity, and then the agricultural numbers arrived. Iowa's Department of Agriculture and Land Stewardship assessed the crop impacts over the following weeks. The conclusion: approximately 37% of Iowa's corn crop showed significant lodging damage, 37%, in a single afternoon. The crop was at the VT stage, maximum wind exposure, minimum structural resilience. 57 million bushels of grain storage capacity were destroyed when the grain bins, the large metal cylinders that hold the harvest after it is picked, were collapsed or shredded by the wind. The harvest that survived the summer had nowhere to go when it was brought in. The total insured losses came in at approximately $7.5 billion. At the time of the event, that made the August 10, 2020 Iowa derecho the costliest in U.S. history. FEMA issued disaster declarations for 27 Iowa counties. The National Guard was activated within hours. 31 states sent mutual aid crews, and the last rural customers in the most severely affected areas waited 11 days for power restoration. 11 days, not because the response was inadequate. Because the damage was that extensive, and the infrastructure required to repair it, the bucket trucks, the replacement poles, the conductor spools, had to come from 31 states to even approach the volume of what was down. That was one event, one derecho. Along this corridor, $7.5 billion. 11 days for the last customers, 37% of a state's crop. 57 million bushels of storage gone. The question that keeps pulling me back to this investigation is not complicated. It is just this: what does a second one cost when it arrives before the first assessment team has reached the first broken line?
The CME Group's corn futures market responds in real time to crop condition reports. What it does not price in at this moment is the training sequence risk, because the training sequence risk is not a standard product of the weather communication architecture. And that communication gap is the next thing I need to show you.
And this is where the story takes a turn that almost every piece of coverage on this setup has completely missed, because the meteorological threat here is real. It is well documented. The ring of fire pattern, the training sequence mechanism, the infrastructure exposure underneath the corridor, all of that is grounded in operational data and peer-reviewed research, and I have tried to walk you through it exactly as it exists. But the infrastructure threat, the part that converts a severe weather event into a regional crisis that lasts not days but months, that depends almost entirely on what happens between Event 1 and Event 2. And the honest answer is that what happens between them is almost nothing, because there is not enough time. Here is how mutual aid works in the electric utility sector and why the timeline matters so much. When a major power outage strikes, something on the scale of the 2020 Iowa derecho, the affected utilities immediately activate mutual aid agreements coordinated through the Edison Electric Institute and, at the federal level, through FEMA. These agreements pull line crews, bucket trucks, transformers, and conductor equipment from utilities across the country. They are extraordinarily effective for what they were designed to do: respond to a single catastrophic event in a defined geographic area. The 2020 Iowa restoration drew crews from 31 states. 31, that is the mutual aid system working at full capacity for a single event scenario. And it still took 11 days for the last rural customers. Now hold that number, 31 states, and think about what it means for a training sequence. The national pool of available line crews during a major event is approximately 45,000, according to Edison Electric Institute documentation. 45,000 sounds like a large number, but it is not divisible across two simultaneous catastrophic wind events in overlapping regions. The crews that restored Iowa in 2020 came from utilities in 31 states. Those utilities had to staff them back up before they could be redeployed. Their equipment had to be serviced, restocked, and repositioned. There is no second pool sitting idle. There is one pool. And in a training sequence where the second event arrives before the first restoration is complete, before a significant fraction of those 31 states' crews have even returned home, the second event does not get 31 states of support. It gets whatever is left. But the crew availability problem, as significant as it is actually not the binding constraint. The binding constraint is transformers. Large power transformers, the substation scale units that step voltage up and down across the transmission system, are not a commodity item. They are custom engineered components, built to specification, weighing hundreds of thousands of pounds, manufactured by a small number of facilities globally. The Department of Energy's Large Power Transformer Vulnerability Assessment, published in 2014 and still operationally relevant, estimated the national spare transformer inventory at fewer than 400 units for a grid with more than 80,000 in service. Lead times for replacement under normal manufacturing conditions run 12 to 24 months, a national spare parts cabinet that was already running low before either storm hit. That is what the grid's resilience actually rests on when a training sequence hits a major corridor. Masood Amin at the University of Minnesota has published extensively on grid resilience and cascading outage risk. And what his research establishes is that the transformer bottleneck is the single most significant long-duration vulnerability in the U.S. Power grid, not because transformers fail in every derecho, they do not, but because when they do fail, in a training sequence scenario, the replacement timeline does not fit inside any mutual aid framework that exists. A crew can replace a broken pole. Nobody can replace a destroyed substation transformer in 48 hours. The physical lead time makes it impossible. And the USTA Farm Service Agency crop loss assessment timeline adds another layer. Standard procedure from disaster declaration to field assessment completion runs 14 to 21 days under single event conditions. That timeline requires passable roads, which require debris clearance, which requires crews. A training sequence restarts the debris situation before the first assessment cycle has closed. Which means some producers in the first event's damage corridor may find their crop insurance documentation timelines running past the eligibility window, not through any failure of a system, but because the physical access required to document the damage was blocked by the second event before the documentation was complete. 3 systems: mutual aid, grid restoration, agricultural assessment, each one designed around single event recovery timelines. Each one facing a scenario its architecture has never been formally tested against. The one time the mutual aid system came closest to a training sequence stress test was June 29, 2012. And what happened that day, and in the 72 hours that followed, produced a pair of FERC and NERC reports that made specific recommendations. Some of those recommendations were implemented. Some were not. And the ones that were not implemented are exactly the ones this current setup is about to test. The June 29th event is sometimes called the Super Derecho. It tracked from Indiana across Ohio, Pennsylvania, and the mid-Atlantic coast, leaving approximately 4.2 million customers without power across 11 states and Washington, D.C. Simultaneously, 22 people died directly from the storm. The death toll from heat-related illness during the subsequent power outage, with temperatures running above 100 degrees Fahrenheit in the Washington and Northern Virginia area, is estimated at an additional 13 to 22 people, depending on the methodology. Every emergency room in the region going critical at the same moment. That is what a simultaneous multi-state outage during a heat wave looks like. The mutual aid system can handle one hospital in crisis, not all of them. And here is the part that almost nobody covered at the time. Within 72 hours of the June 29th event, before full restoration was complete in the most severely affected rural areas across West Virginia, Ohio, and Virginia, a second organized convective system tracked across portions of the Ohio Valley corridor. Not a full-scale derecho of the same magnitude, but enough to compound the damage situation in areas that were already dark, already cleared of emergency resources, already waiting for crews that were in the field on the first event's restoration. The FERC post-event report identified mutual aid resource coordination as a critical gap. The language in the report was careful and bureaucratic, as FERC language tends to be, but the finding was unambiguous. The simultaneous multi-day state scope of the June 29th event, quote, exceeded the design coordination capacity of existing regional mutual aid frameworks, end quote. NERC's reliability assessment echoed this finding, specifically flagging the compound event scenario as a gap in the existing resilience framework. The recommendations that came out of those reports included accelerated mutual aid pre-positioning protocols. The idea that when a training sequence is forecast, crews and equipment should be pre-staged in regions outside the immediate damage zone before the second event, rather than waiting for it to hit and then requesting mutual aid. They included expanded spare transformer stockpiling under a dedicated federal strategic reserve program, and they included updated communication protocols for compound convective sequences, standardized products that would allow the NWS and the SPC to communicate training sequence risk to utilities, emergency managers, and the public as an integrated threat rather than a series of separate events. John Neese at Penn State provided atmospheric analysis of the 2012 event that helped establish the connection between the boundary behavior and the training potential. His work, alongside the FERC and NERC reports, created a fairly complete picture of what the gap looked like and what it would cost to close it. But closing a gap requires sustained institutional attention. And in the decade plus since 2012, the pre-positioning protocols were partially developed and then quietly deprioritized in subsequent budget cycles. The transformer stockpiling program was authorized at a scale far below what the DOE assessment identified as the minimum adequate reserve. The compound convective sequence communication products were discussed and not standardized. The atmospheric pattern does not check budget cycles before deciding to hold a boundary quasi-stationary for 96 hours. So where does the second system actually stand in the current model output? Because I want to be precise about this, because precision is what distinguishes a legitimate operational concern from alarm without evidence. Here is what the model consensus shows, and here is where the uncertainty lives. The GFS ensemble mean, the ensemble of runs from the global forecast system, which averages across dozens of model solutions to smooth out individual run noise, shows a second organized convective threat in the 72-hour window from the current analysis time. The track consensus across the ensemble members falls within approximately 150 miles of the first event's forecast corridor. That is a meaningful constraint on the uncertainty, not a single-line forecast, but a range of solutions clustering in the same general zone. The European Center for Medium-Range Weather Forecasts, the ECMWF, runs its own operational model and its own ensemble, and these are widely regarded as the most accurate medium-range guidance available globally. The ECMWF operational run concurs with the GFS on the boundary position and the instability axis. Where the two models diverge is on the timing of the Pacific Trough, the large-scale upper-level feature that would finally break down the ring of fire pattern and shift the boundary. The GFS has the trough arriving approximately 12 to 24 hours earlier than the ECMWF. That timing difference is not trivial. A 12 to 24-hour difference in when the pattern breaks determines whether a second, fully organized MCS has time to develop and track the corridor, or whether the atmosphere begins to stabilize before it can mature. The SPC's Day 3 and Day 4 outlooks have elevated severe weather probability over the Central Plains for the relevant window. The language in the Day 3 outlook discussion, and I want to be specific here because the AFD language is operationally significant, notes potential for organized convective modes in the same general corridor. That phrasing, organized convective modes, is SPC shorthand for the kind of structured system that produces widespread, long-duration wind damage rather than scattered cells. It is not a certainty. Forecasters are not making a certain claim. But the probability signal is there, and in the context of a quasi-stationary boundary and a fully recharged warm sector, it is a probability signal worth taking seriously. Think about what a probability cone looks like on a hurricane track forecast. The cone is not one line. It is a range of lines, every line inside the cone representing a physically possible track, every community underneath the cone a real place where real decisions have to be made before the storm arrives. The ensemble spread on the second system's track functions the same way. Every member inside that 150-mile clustering zone is a real community. And the communities that were in the damage corridor of Event 1 are, by definition, inside that clustering zone. Here is what I will say with confidence, and here is what I will not claim certainty about. What I can say with confidence: the atmospheric environment, the boundary position, the instability, the moisture loading, the upper level pattern is supportive of a second organized convective event in the 72 to 96 hour window. The models with the best track records at this lead time are showing that environment persisting. What I cannot say with certainty, the exact track, the exact timing, or the exact intensity of that second event, those are genuinely uncertain at this range. And a careful person holds that uncertainty in one hand alongside the probability signal in the other. What I can say with a great deal of confidence is that the atmospheric uncertainty about the second event's track is only one layer of the uncertainty in this setup. The other layer is not uncertain at all, and it is the layer that, if you are in this corridor, matters most right now. Roger Elmore spent years at Iowa State University Extension studying how corn responds to wind events at different growth stages. His research on lodging, the term agronomists use when wind forces a corn plant to bend or snap at or near the base, established something that should be part of every severe weather briefing for agricultural regions in June and July, but almost never is. The VT stage, tassel. It is the moment when a corn plant has achieved its maximum height, when the pollen-bearing tassel at the top of the stalk has emerged or is about to emerge, and when grain fill, the process of actually producing the kernels that become the harvest, has not yet begun. At VT, the corn plant is at its aerodynamic worst, fully extended, maximum surface area exposed to wind, and structurally committed to a height it cannot reduce. A 6-foot stalk with a sail at the top and nothing but a root ball holding it to the ground. That is what a derecho encounters when it crosses an Iowa cornfield in late June or early July. What Elmore's research documents is that lodging damage at or near the VT stage is categorically different from lodging damage earlier or later in the season. Earlier in the season, the plant may recover. It can sometimes right itself, particularly if the damage is from bending rather than snapping. Later in the season, after grain fill is substantially complete, the harvest is partially protected even if the plant goes down. At VT, there is no recovery and there is no partial protection. The plant snaps. The tassel is destroyed. Pollination does not happen. The grain fill that would have produced the harvest never begins. Every input, the seed, the fertilizer, the herbicide, the labor, the fuel, is a loss. The field produces nothing. The USDA National Agricultural Statistics Service tracks crop progress weekly, and the current reports for Iowa, Illinois, Nebraska, and Kansas show a substantial percentage of corn at or approaching the VT growth stage during the window of this forecast setup. The exact figures update each Monday, and I would encourage you to pull the current report directly from the NASS website. This is public data, and you can see the state-by-state progress with your own eyes. What the current report shows, in combination with the forecast window, is that this setup is arriving at the worst possible moment for corn that has survived the summer. Now layer the crop insurance dimension on top of that. The USDA Risk Management Agency standard provisions for crop insurance claims require loss documentation within specific windows following a disaster event. For certain claim categories, the documentation window can be as short as 72 hours from the event. That documentation requires field access. Field access requires passable roads. Passable roads require debris clearance. And debris clearance in the aftermath of a derecho that has brought down hundreds of thousands of trees and power lines across a multi-county area is measured in days to weeks. A second derecho arriving before that clearance is complete does not just add more damage. It resets the documentation clock for the first event in the areas it affects. Some producers could find themselves unable to document losses from Event 1 within the required window because Event 2 has made their fields inaccessible again. The scale of the geographic exposure here is worth stating plainly. Iowa, Illinois, Indiana, and Nebraska together produce approximately 55% of U.S. corn output. The forecast corridor does not cover all of those states equally, but it covers enough of them during the most vulnerable growth stage that the commodity market implications of a training sequence are not domestic. The United States supplies approximately 32% of global corn exports. A training sequence that significantly damages the crop in the central corn belt is not a story that ends at the Iowa state line.
The CME Group's corn futures market responds in real time to crop condition reports. What it does not price in, at this moment, is the training sequence risk, because the training sequence risk is not a standard product of the weather communication architecture. And that communication gap is the next thing I need to show you.
There is a specific kind of institutional gap that is harder to see than a broken piece of equipment or a failed policy decision. It is the gap between what a system was designed to handle and what it is now being asked to handle, a gap that nobody created on purpose, that nobody is hiding, but that exists because the system was built in one era and the threat has shifted in another. The NWS Severe Weather Warning Architecture is one of the most sophisticated public safety systems in the world. I want to be clear about that before I explain where its edges are. The tornado warning, the severe thunderstorm warning, the particularly dangerous situation designation, the SPC convective outlook system. These products save lives. The improvements to that system over the past 20 years have been genuine and significant. The completion of the dual polarization radar upgrade across the NEXRAD network in 2013 fundamentally changed what forecasters can see inside a storm. The implementation of the high-resolution rapid refresh model, the HRR, gave operational meteorologists short-range guidance at a 1-kilometer resolution that simply did not exist a decade and a half ago. But the warning architecture was designed around an isolated event paradigm. A tornado warning tells you, a tornado is occurring or imminent in this location. A severe thunderstorm warning tells you, dangerous wind or hail is occurring or imminent in this location. A particularly dangerous situation watch tells you, conditions are favorable for significant tornadoes or widespread severe weather in this area today. What none of these products tells you, and what no standardized NWS product currently tells you, is this. There will be 2 or 3 of these events, days apart, along the same track, before the atmospheric pattern breaks. The compound nature of the training sequence is not communicated through any existing warning architecture product. Each event is warned as if it is an isolated severe weather threat. Think about what that means for a utility operator in Omaha making a decision about whether to pre-stage bucket trucks and conductor equipment. The Day 1 convective outlook tells her there is a moderate risk of severe weather tomorrow. It does not tell her that the moderate risk is likely to recur 2 days later along the same corridor, because that is a forecast characteristic of the atmospheric pattern, not of the individual event, and no standard product exists to convey it. She makes her crew and equipment decisions based on an isolated event framework, because that is the framework the communication architecture provides. Harold Brooks at NOAA's National Severe Storms Laboratory has studied warning effectiveness and lead time extensively, and his research establishes that the average lead time for a derecho scale severe thunderstorm warning is 14 to 22 minutes. That is adequate lead time for an individual shelter decision. It is not adequate lead time for grid prepositioning, for agricultural equipment relocation, or for the logistical preparation required to position mutual aid resources before a training sequence's second event. Those decisions require information at the 48 to 96 hour scale, framed in a way that communicates the compound nature of the threat. And there is an additional technical limitation the 2020 Iowa event exposed. NWS post-event reviews noted that the August 10th system's rapid organization, the speed with which it intensified into a full-scale derecho, exceeded model guidance by approximately 60 to 90 minutes. The effective warning window compressed, not because the forecasters missed anything, because the atmosphere moved faster than the initialization cycle of the guidance products being used in operational practice. The warning system is a fire alarm designed for one fire. It tells you there is a fire in this room today. It does not tell you there will be another fire in this same room on Thursday, and that the building between now and Thursday is going to fill with smoke that limits how quickly Thursday's response can move. Solving this gap requires developing standardized compound event communication products, a recognized severe weather product class that explicitly communicates training sequence risk to emergency managers, utilities, and the public as an integrated threat. Meteorologists at the SPC and within the broader NWS research community are aware of this gap. There are people actively working on it, but awareness is not the same as a deployed product. And a deployed product that does not yet exist cannot help the communities under this corridor right now. Let me map what the cascade from Event 1 actually looks like in operational terms, because the abstract framing of compound consequences does not convey what it means for the people inside it. A derecho at the intensity level of the 2020 Iowa event moves through a major metro area in approximately 2 to 4 hours. Window, it downs transmission lines, collapses distribution poles, destroys substation equipment, collapses grain bins, uproots trees across thousands of miles of road right-of-way, and damages cellular infrastructure across a multi-county swath. The moment the power goes out, 4 separate cascades begin simultaneously. The cellular cascade starts immediately. Most cellular towers carry 4 to 8 hours of backup power, battery banks that sustain the tower through short outages. FCC rules require 48 hours of backup for towers in certain high priority categories, but actual deployment is highly variable, and in rural areas of the Midwest corridor, 4 to 8 hour batteries are common. When those batteries discharge, the towers go dark. Emergency alert delivery degrades. The warning broadcast system for Event 2, arriving perhaps 48 to 72 hours later, has reduced reach in exactly the communities that need it most, because the cellular infrastructure that carries wireless emergency alerts is damaged from Event 1. The hospital cascade begins within the first 4 hours. Most hospitals operate backup generators fueled by on-site diesel tanks. The Joint Commission standard calls for 96 hours of fuel. Actual inventory varies. And in 2020, multiple Iowa hospitals reported generator fuel resupply challenges as the restoration timeline stretched past initial projections. Resupply requires diesel fuel trucks, which require passable roads, which require debris clearance. The table with 4 legs. Event 1 kicks out 2 of them before Event 2 has even formed on the radar. The heat cascade begins within 24 to 48 hours, and it is the most lethal. CDC data establishes that excess mortality begins to climb within 24 to 48 hours of a power outage during heat events when daytime temperatures exceed 90 degrees Fahrenheit. The same heat dome generating the instability that produced Event 1 is still parked over the region during the outage period. It is still pushing daytime highs into the mid to upper 90s. Without air conditioning, without fans, without refrigeration for medications, the elderly and the medically vulnerable face a mortality risk that is both predictable and preventable, and that becomes harder to address as emergency response resources are diverted to Event 2's immediate aftermath. The food supply cascade follows within 48 to 72 hours. Refrigeration fails in grocery stores and residential units within 4 hours of outage. USDA Food and Nutrition Service data indicates that refrigerated food resupply to affected areas typically requires 48 to 72 hours of road access to restore. In a training sequence where road debris clearance from Event 1 is incomplete when Event 2 hits, the resupply timeline from Event 2 extends further still. Iowa DOT's after-action analysis from the 2020 derecho estimated 48 to 72 hours to clear primary routes following that event. Secondary and rural roads took 7 to 14 days. In a training sequence, the secondary and rural road clearance from Event 1, the roads that connect farm fields to assessment teams, that connect rural residents to emergency services, that connect repair crews to damaged transmission segments, is still incomplete when Event 2 deposits a second layer of debris on top of it. None of these cascades are individually catastrophic in isolation. Each one is a manageable emergency within existing frameworks, but they do not occur in isolation. They occur simultaneously in a region where the emergency response resources that address each one are the same resources being drawn on for every other cascade at the same time. And in a training sequence, those resources face a second activation demand before the first activation has drawn down. Anytime a weather event of this scale builds toward a populated, economically significant region, the fringe explanations start circulating. I want to address the specific ones I have seen around this setup directly, not because they deserve extended engagement, but because the people asking deserve an actual answer, and because there is something genuinely interesting buried inside the question if you look at it the right way. The claims circulating around this setup fall into 2 main categories. The first is HAARP, the High Frequency Active Auroral Research Program, a research facility in Alaska that studies the ionosphere using high-frequency radio waves. The claim is that HAARP is being used to steer, intensify, or direct the derecho sequence toward agricultural regions. The second category is broader weather modification. Chemtrail seeding to intensify convection, directed energy weapons, some combination of the above. Let me deal with HAARP first, because the physics is the most direct. The HAARP facility's maximum output is 3.6 megawatts. That is the documented, public, verifiable upper bound of what the system can produce. A single mesoscale convective system, the kind of organized storm system we have been discussing, releases energy on the order of 10 to the 18th joules per day. A flashlight pointed at a freight train, that is the scale mismatch. 12 orders of magnitude separate HAARP's maximum output from the energy involved in a derecho-producing MCS. There is no physical mechanism by which a 3.6 megawatt signal applied to the ionosphere produces or steers a convective system operating at 10 to the 18th joules. The energy is not there, the mechanism does not exist. But here is where the fringe framing gets unexpectedly interesting, because there is one alternative explanation for human influence on convective systems that has a genuine peer-reviewed scientific substrate. Cloud seeding. It exists, it is practiced, it is not secret. Operational cloud seeding programs are active in Wyoming, Utah, Colorado, and several other western states, targeting snowpack enhancement through silver iodide particle injection into winter storm systems. These programs are documented, publicly regulated, and studied by the Weather Modification Association. Their maximum precipitation enhancement under optimal conditions is estimated at 10 to 15%, not the creation of a storm, but a modest augmentation of precipitation from a storm that would have occurred anyway. The mechanism, introducing hygroscopic nuclei that facilitate ice crystal formation, is entirely different from the kind of convective intensification that produces a derecho. You cannot seed your way to a bow echo. A garden hose used carefully in the right conditions can water a garden. It cannot produce a flood, so the conspiracy explanation is wrong. The physical mechanism does not support it, and the energy arithmetic makes it impossible. But the alarm underlying it is not wrong. Because there is a real human fingerprint on this event, it is just not the one the fringe claims are pointing at. Victor Gansini and Thomas Brooks published a study in NPG Climate and Atmospheric Science in 2019 that found statistically significant increases in severe weather days across the central United States in spring and early summer over the past 3 decades. The signal is consistent with projected changes in the upper-level atmospheric pattern under continued warming. Specifically, a tendency for the jet stream to take configurations that support ring of fire patterns more frequently, and for the heat dome events that drive the instability boundary to become more intense and more persistent. The warming signal on ring of fire frequency is real. It is peer-reviewed. It is the actual human fingerprint on the increased recurrence of this threat. Not a government facility in Alaska manipulating the ionosphere. Not seeding programs operating in a season and a mechanism that do not produce convective storms. A decades-long trend in the large-scale atmospheric pattern driven by the accumulation of greenhouse gases that is making the environment conducive to ring of fire setups more common and the events themselves more intense. And alongside that warming signal sits the policy fingerprint. A Midwest transmission grid with an average age of 42 years, a federal transformer stockpiling program authorized at a fraction of the identified need, and a compound event communication architecture that has not been standardized despite post-event recommendations going back more than a decade. The conspiracy explanation is wrong. The actual explanation, a warming-driven pattern trend layered on top of a policy gap, is alarming enough without embellishment. And it raises a direct question about what the current setup actually means going forward, because there are at least 3 honest ways to read this evidence. And each one has real implications for the decisions being made right now. Before I walk through those 3 interpretations, there is one more thread of evidence I want to bring into this investigation, because it places the current U.S. threat in a context that makes the policy gap harder to dismiss as an abstract domestic concern. In July of 2021, the Ahr and Erft river basins in western Germany, a region that had been heavily settled and developed for centuries under the assumption that its flood risk was well characterized and well managed, experienced what became the deadliest natural disaster in German post-war history. 197 people died, 46 billion euros in damage was recorded. And the mechanism, when the European Severe Storms Laboratory and the Deutscher Wetterdienst, the German Meteorological Service, completed their post-event analyses, was not primarily about rainfall totals. It was about training. A quasi-stationary low-pressure system over Western Europe produced a sequence of organized convective systems that tracked repeatedly over the same river catchment areas. Not one extreme rainfall event. A training sequence of extreme rainfall events, each one contributing to a river system that had no capacity remaining from the previous pulse. The structural parallel to what we are discussing for the U.S. Central corridor is exact, a quasi-stationary boundary, successive organized convective systems riding the same track, each one arriving before the affected system. In Germany, the rivers. In the US, the grid and the crop has recovered from the previous event. The Deutscher Wetterdienst's post-event assessment concluded that the warning lead time for the training sequence was operationally adequate. The forecasts existed. The warnings were issued. The problem was that the communication architecture failed to convey the compound nature of the threat, that it was not one heavy rain event, but a sequence, that the rivers would not have time to recede between events, that the cumulative impact would exceed any single event by a factor that no isolated event framework could anticipate. Sound familiar? Germany and Belgium responded with a major reassessment of their severe weather warning communication architecture. New compound event products were developed. The language around multi-event sequences was formalized. Institutional memory was built into the warning system in a way that had not existed before 2021. The US, policy response to its own compound event near misses. The 2012 Super Derecho sequence, the May 2024 Iowa and Illinois training events, has been slower. The FERC and NERC recommendations from 2012 remain partially implemented. The DOE Grid Resilience and Innovation Partnerships Program, the GRIP program, funded at $3 billion under the Infrastructure Investment and Jobs Act, is a genuine commitment to grid hardening. But $3 billion spread across a national grid with identified resilience gaps estimated at multiples of that figure by the American Society of Civil Engineers is a start, not a solution.
The atmospheric pattern does not distinguish between countries that have updated their communication architecture and countries that have not. It does not pause for budget cycles or policy timelines. It assembles, it holds, it trains. And what the international comparison shows is that the compound event warning gap is a solvable problem because other countries have begun solving it. The question is whether the U.S. warning and infrastructure system catches up before the next major training sequence or during it. Which brings us to the three honest interpretations of what the current setup means.
The most reassuring, honest interpretation of this setup is not a straw man. It deserves real weight, and I am going to give it that. Here is the case, stated as fairly as I can state it. The meteorological forecasting system watching this setup is significantly more capable than anything that existed during the derecho events most commonly used as historical reference points. The completion of the dual polarization upgrade across the NexRad network changed what forecasters can see inside convective systems, not marginally, but fundamentally. Dual pol radar can distinguish rain from hail, wet snow from dry snow, and biological targets from meteorological ones. It gives operational meteorologists a three-dimensional view of storm structure that single polarization radar simply could not provide. The HER model runs every hour at 1 kilometer resolution, providing short-range guidance that allows the SPC and local NWS offices to identify convective mode, the difference between isolated supercells and organized linear systems, with a specificity that was not available 15 years ago. What this means practically is that the warning lead time for this event, whatever its ultimate intensity, is likely to be better than it was for the August 10, 2020 derecho. That event's rapid organization compressed the warning window. The current setup has been on the model's radar, literally and figuratively, for several days. Emergency managers in Kansas, Nebraska, Iowa, and Illinois have had time to activate pre-event preparation protocols that were not available on a few hours' notice in 2020. The mutual aid system, for all the capacity constraints I have documented, did restore power to approximately 4 million customers in Iowa following the 2020 event, the most destructive single derecho in U.S. history within 11 days for the vast majority of affected customers. That is not a trivial achievement. The system held, the crews came. The infrastructure, however battered, was rebuilt. Crops have crop insurance. The Federal Crop Insurance Program, administered through the USDA Risk Management Agency and delivered through private insurers, was designed precisely for catastrophic loss events. The 2020 Iowa derecho resulted in approximately $2.7 billion in crop insurance payouts, not full recovery for every producer, but a meaningful floor under the most severe losses. Producers who experienced total field losses from lodging received indemnities that in many cases allowed them to continue farming the following season. The populations of Kansas City, Omaha, and Des Moines have lived with severe weather risk for generations. Local emergency management agencies in these cities have plans, have practiced, have stockpiled resources, and have relationships with state emergency management that allow faster activation than less prepared regions. The individual shelter decisions that a well-issued severe thunderstorm warning enables, move to an interior room, stay away from windows, avoid travel, are decisions that millions of people along this corridor have made before and will make effectively when the warnings come. This interpretation is not wrong, it is fair. It accounts for the real improvements in forecasting capability, the real resilience of the mutual aid system under single event conditions, the real existence of risk transfer mechanisms like crop insurance, and the real preparedness of major metropolitan populations that have experienced severe weather before. A careful person holds this interpretation in one hand, but a careful person holds it alongside the evidence. And the evidence in this investigation does not most directly point here. The intermediate interpretation is where the peer-reviewed research, the operational data, and the documented precedents from previous compound convective sequences converge. And I want to be precise about what this interpretation claims and does not claim. It does not claim that this setup will produce an unprecedented catastrophe. It claims that the training sequence scenario, specifically the scenario in which a second organized convective system tracks within the damage corridor of the first within 48 to 72 hours, genuinely exceeds the design capacity of the mutual aid, grid restoration, and agricultural assessment systems as they currently exist. Not catastrophically, but measurably and consequentially. The specific thresholds where exceedance is most likely are well defined in the evidence. The mutual aid crew pool, approximately 45,000 national line workers, is not divisible across two simultaneous major restoration events in overlapping regions. If the first event activates a significant fraction of that pool, the second event encounters a degraded resource availability. That is not speculation. It is arithmetic applied to documented system capacity. The transformer inventory, fewer than 400 national spares for a grid with 80,000 in service, means that any substation transformer losses in the first event cannot be replaced before the second event. The repair hierarchy for grid restoration prioritizes bulk transmission first, then distribution. If bulk transmission equipment sustains damage that requires transformer replacement, the affected communities in those segments face a restoration timeline measured not in days but in months, regardless of how many line crews are in the field. That is a hard constraint imposed by manufacturing lead times, not by any failure of the response effort. The crop insurance documentation timeline, 72 hours for certain loss categories requiring field access, runs directly into the road clearance timeline from Event 1. Iowa DOT documented 48 to 72 hour primary road clearance following 2020. If a second event arrives at the 72-hour mark or before primary clearance is complete, producers in the overlap zone of both events face a documentation access problem that the insurance framework was not designed to accommodate. None of these are worst-case assumptions. They are median-case applications of documented system constraints to the training sequence scenario. The intermediate interpretation, grounded in the peer-reviewed work of Gensini and Ashley on Ring of Fire training frequency, the DOE Large Power Transformer Assessment, the FERC post-2012 analysis, and the Iowa DOT after-action documentation, suggests a multi-week recovery timeline in the most severely affected areas, with specific pockets of extended outage where transformer damage coincides with the deepest rural reach of the affected corridor. This is the interpretation the published literature most directly supports. Not every outcome of the current setup reaches this level. Some will resolve closer to interpretation 1. But the compound risk, the training sequence risk, has a documented probability that warrants this framing as the weight of the evidence's landing point. The worst case, grounded in physics rather than speculation, requires three things to be true simultaneously. The atmospheric boundary holds quasi-stationary for 96 plus hours. 2 or 3 derecho scale organized convective systems develop, mature, and track within a corridor narrow enough that their damage swaths significantly overlap. And at least 2 of those events hit major transmission infrastructure, producing transformer losses in the bulk system. None of these 3 conditions is physically impossible. Each one is consistent with the observable atmospheric setup. The boundary's quasi-stationarity is being forecast by the models with meaningful confidence. The potential for 2 or 3 organized convective systems is embedded in the Ring of Fire training climatology, Gensini and Ashley's 38% recurrence rate in quasi-stationary setups. The corridor concentration, the overlap between successive damage swaths, is the one condition most dependent on the details of the pattern evolution, and it is also the one with the most genuine uncertainty at this forecast range. But let me be precise about what I mean by worst case. Not a hypothetical calamity beyond all historical precedent in every dimension. A specific, physically bounded outcome. A worst case for this setup looks like this. 2 derecho scale events in under 72 hours, tracking within 100 miles of each other across the Iowa-Illinois-Indiana corridor. Combined damage swaths covering 500 to 700 miles of power infrastructure in overlapping zones. Transformer losses at 4 to 6 major substations in the overlap zone, a number well within the historical range for derecho events of the relevant intensity. National spare inventory cannot address those losses within the lead times that matter for restoration. Affected communities in the overlap zone, not all of them, but those in the deepest rural segments of the overlap, face extended outage scenarios measured in weeks to months rather than days. Simultaneously, corn at VT stage in both events' corridors sustains near total lodging damage across 2 to 3 million acres. The crop insurance documentation system is overwhelmed by the compound access problem. Agricultural losses approach or exceed the 2020 benchmark, $3.8 billion in Iowa alone, across a broader multi-state geography. And the cellular and hospital cascades from Part 11 play out across a larger area than any single event produces, with reduced response capacity because mutual aid resources from the first event have not fully demobilized before the second activation demand arrives. There is no historical precedent for 3 derecho scale events in under 100 hours along an overlapping corridor, which means the mutual aid frameworks, the grid restoration protocols, and the compound event communication products have literally never been stress tested against this scenario. The scenario is physically possible. The models are not forecasting it as the most probable outcome. But in a compound threat assessment, what a physically possible worst case costs if it materializes, weighed against what it costs to over-prepare, is always a relevant calculation. And only continued observation of the boundary behavior, the low-level jet evolution, and the model consensus over the next 48 to 72 hours will establish which of these 3 interpretations best describes the reality unfolding across the central United States. I want to close the analytical portion of this investigation with something that I find more useful than a confident prediction, an honest accounting of what we actually know, what is genuinely uncertain, and what specific information would resolve that uncertainty. What is confirmed? The ring of fire pattern is active and documented by operational forecasting systems right now. The instability corridor, CAPE in the 2000 to 4000 range, surface dew points in the upper 60s to low 70s, is real and consistent with historical derecho producing setups. At least one significant organized convective event is operationally likely within the 72-hour window. The geographic corridor under the forecast track includes critical agricultural infrastructure at the VT growth stage and power transmission infrastructure at a documented age and vulnerability level. The mutual aid system, the grid restoration architecture, and the agricultural assessment framework all carry single event design assumptions that a training sequence would stress. The warning communication architecture does not currently have a standardized product for training sequence risk. All of that is confirmed by the operational data and the documented record. None of it is contested. What is genuinely uncertain? Whether the boundary holds quasi-stationary long enough for a second, fully organized convective system to develop and mature, the difference between a training sequence and an isolated event. Whether that second system, if it develops, tracks within the damage corridor of the first, or whether the track diverges enough to distribute the compound impact across a wider area with less overlap. Whether grid operators will choose to pre-stage mutual aid resources and spare equipment ahead of the second event based on the training sequence forecast environment, or whether the institutional response will default to isolated event protocols, and the exact intensity and track of any individual event within the sequence, which carries genuine model uncertainty at the 48 to 96 hour range. What specific information would resolve the key uncertainties? The SPC's Day 3 and Day 4 convective outlooks. Watch for language around boundary persistence and organized convective mode. The ECMWF and GFS 12-hour runs, specifically whether the model consensus on the Pacific trough timing converges or diverges, because that timing determines whether the pattern breaks before or after a second event organizes. NWS area forecast discussions from NWS Wichita, Kansas City, and Omaha. The AFDs from those offices will carry the most operationally specific language about how forecasters are reading the boundary behavior. And the USDA Weekly Crop Progress Report, which updates each Monday, will tell you exactly what percentage of the corn in each state was at or past the VT stage when this setup arrived. All of this is public. All of it is verifiable. You can pull the SPC outlooks at spc.ogov. You can read the area forecast discussions at weather.gov, navigate to the relevant office, and find the AFD in the forecast product menu. You can access the ECMWF public output through the Copernicus Climate Data Service. The operational data that determines how this story unfolds is available to anyone who wants to follow it in real time. Here is where this investigation stands. A ring of fire pattern is active across the central United States, generating the most volatile instability boundary this season has produced. The training sequence mechanism, the atmospheric assembly line that sends successive organized convective systems along the same track before the pattern shifts, is a documented and climatologically credible feature of this setup. The corridor underneath the forecast track carries power infrastructure at documented age and vulnerability, crops at the single most wind-vulnerable growth stage, and populations served by warning and mutual aid systems that were built for isolated events. The mutual aid system's single event capacity is real. The NWS warning system's improvements are real. The crop insurance safety net is real. And none of those real things was designed for what a training sequence delivers before the first one's damage has been assessed. The data does not tell us which of the 3 interpretations will prove correct. That is an honest statement, not a hedge. What the data tells us is what each interpretation costs if it turns out to be wrong, and the asymmetry in that calculation is worth sitting with. There are people making decisions right now in the corridor under this forecast. Grid operators deciding whether to pre-stage equipment. Emergency managers deciding whether to activate pre-event protocols. Farmers deciding whether there is anything they can do to protect a crop that the atmosphere may not allow them to protect. Those decisions are being made inside the uncertainty. And the most useful thing this investigation can do is be precise about where the uncertainty lives.
We will be watching the boundary. We will be watching the model consensus on the trough timing. We will be watching the SPC outlooks through the forecast window. And when this story moves, when the first event verifies, when the second system either organizes or does not, when the model uncertainty resolves into the reality that the people in this corridor are living, we will be here. The ring is lit. The trains are loading. We'll keep watching the track.